Okay, pre-calc students, we're on section 8.2 on part C, where we're solving a system of 3 equations and 3 variables. Some things you can do with these are change the order. You can multiply a constant to an equation. You can add 2 equations together and replace it with one of the equations that you added. When you solve, it's the same idea as what you did in section 8.1 with solving a system of linear equations. You're just going to add them together. Best thing to do is if you have the x term as a coefficient of 1 in row 1. So you can switch them around so you have that top left corner having a coefficient of 1. And you can also eliminate the x's in row 2 and 3 by doing the linear combination. And then you can go back and back substitution and find all of your variables in the end. So let's do an example. We have this one here, 3 equations, 3 unknowns. We're going to start by taking these first 2 rows, row 1 and row 2, and adding them together. You notice you do have a 1 as the coefficient in the first equation and a negative 1 as a coefficient in the second equation. When you just combine those, the x's will disappear. So we're going to put the first equation and second equation off to the side. The variables are all lined up. And when you do linear combination, first ones are gone, and you're left with y plus 3z equals 5. That's going to sub back in to the second equation. It could sub back in for either place, but the first equation, we like the fact that it has a 1 in the coefficient of the x, so that one's fine. The second equation is now y plus 3z equals 5. We rewrite this whole system again. Now we're going to look to eliminate the x in the second position now. We're going to combine rows 1 and 3. In order to make that x disappear, you're going to multiply row 1 by negative 2. So if you multiply everything in row 1 by negative 2, that's negative 2x plus 4y minus 6z equals negative 18. And row 3 is fine the way it is because now the x's will cancel. When you combine these using linear combination, the x's disappear and you're left with negative y minus z equals negative 1. And that's going to go back in for either 1 or 3, and we'll put it in for 3. So 1 and 2 are the same. And row 3 now is negative y minus z equals negative 1. We've now eliminated all the x's except for the first equation. Now we're going to eliminate this y down here in the third equation, so it's going to line up where you have it as a little diagonal. So if we take row 2 and row 3 and add them together, you're going to notice that it's already lined up with our linear combination where the y's are still disappearing. If it didn't, you could multiply by a common factor and get rid of those. This time the y's are gone. You're left with 2z equals 4. Or you can even simplify that down by dividing both sides by 2 to z equals 2. And that will go back in to row 3. So now our system, the first row has all 3 variables. The second row only has y's and z's. And the last row, you now have one of the answers, z equals 2. So now you can take this z and plug it back in order to find the other 2 variables. If you plug that into the second equation, you can solve for y. So this is y plus 6 equals 5. If you subtract 6 from both sides, you get y equals negative 1. And then if you take the z and the y and plug them both into the first equation, you're going to be able to find x. So this is x minus 2y plus 3z equals 9. That's x plus 2 plus 6 equals 9. And 2 plus 6 is 8. And when you subtract it to the other side, you get x equals 1. So altogether now we have a system of equations solving down for the x is 1, the y is negative 1, and the z is 2. And that's the solution that's true for all 3 equations. So that would be the solution to the system.